So far, we've been talking about operations such as addition, subtraction, and multiplication. Today, we're going to be looking at division. So you'll notice in example one, there's a couple of different notations that we can use to recognize that the operation that we want to do is division. And we're just going to set these up and then we'll talk about domain and how the domain is different for a function when we're using division. So for example one, we've got a whole bunch of different functions here. And I'm going to look to see, well, what does g of x divided by f of x look like? So if I substitute in my g of x in the numerator is 2x plus 5, my f of x in the denominator would be 3x. And this notation looks pretty similar to what the notation was that we looked at last week. When you have a g over h of x, that really just can be rewritten as g of x over h of x. So just a different way of seeing the division notation. So if I set that fraction up, g of x is 2x plus 5 divided by h of x, which is 8 minus 3x. F of x divided by p of x, so our f of x is 3x, and our p of x is x squared minus x minus 12. And just notation that, again, looks a little bit different, but again, that's pretty straightforward that it's indicating that we want to divide here. Q of x divided by p of x, even though that this is written in horizontal format, when we set up our fraction, we want to set it up like we did for a, b, and c. So q of x on the top is x minus 4, and p of x on the bottom is x squared minus x minus 12. Okay, so pretty straightforward, just division. We want to just set our functions up as fractions. Something that is going to be different for these types of problems is that we're going to have some domain restrictions, meaning that when we go to write a domain of a divided function, we have to be careful about what's going on in the denominator, because we know that in the denominator of a fraction, we can never have a 0. So that means that there's going to be some sort of restriction on the domain, meaning that there's going to be some sort of value that we're going to skip over. So there might be one or more values we will skip over. And again, the domain of this function does not include x values where the denominator is equal to 0. So that's going to be kind of the places that we're going to concentrate on where we're getting our domain restrictions. Okay, so for example A, if we go back up to our example A up here, our function that we want to find our domain of is 2x plus 5 over 3x. So basically, we want to look at the denominator. We want to figure out, well, where is the denominator equal to 0? So our restriction is going to be where our denominator, so our denominator of this fraction is 3x, is equal to 0. So I'm just going to solve this like it would be a linear equation I'm solving for x. So divide by 3. This is telling me that my restriction is that x is equal to 0, which means that in the domain, this is going to be the value that I want to skip over. And we've talked a lot about domains in terms of graphs, and what that means is that when we skip over the value, this is going to be where we're going to use the u for the domain. So that means that basically the domain of this function could be anything. It could be anything negative or anything positive. It just can't be 0, because if I went to plug 0 back in here, that would give me a 0 in the denominator. We know that we can't have that. So when I write the domain, it's basically going to be all real numbers, so negative infinity to positive infinity, except for 0. So in interval notation, that would be negative infinity to 0. I'm going to use an open parentheses because I don't want to include this value. And then I'm going to put the u, and then I'm going to put the open parenthesis and then the 0 again, and I'm going to put the infinity. So that basically tells me my domain is anything from negative infinity to positive infinity, except I'm skipping over 0. And in set notation, what that would look like, x such that x is an element of the real numbers, and then I'm just literally going to put x can't be equal to 0. So that's what it would look like in interval notation. That's what it would look like in set notation. And you can use whatever you're more comfortable with. Okay, so let's look at example B. So our example B up here was 2x plus 5 over 8 minus 3x. So my restriction is going to be where 8 minus 3x is equal to 0. So that will be 8 is equal to 3x, and that's going to give me x is equal to 8/3. So again, this is going to be the value that I'm going to skip over in my domain. So my domain is going to be all real numbers, so negative infinity to positive infinity, except for this 8/3. So I'm going to put the 8/3 basically where I put the 0 in the last domain that we just wrote in example A. So negative infinity to 8/3, skip over 8/3, start at 8/3 again, and then go to positive infinity. And in set notation, that would be x, such that x is an element of the real numbers. X can't be equal to 8/3. Okay, so let's look at example C. This one's going to be a little bit different because you'll notice that in the denominator, there's going to be a quadratic. So we want to see if this quadratic is going to factor, and then we'll figure out our restrictions from there. So I'm going to go back up here and I'm going to say, okay, well, I know that x squared minus x minus 12 factors into an x minus 4 and an x plus 3. So when I go to find my domain restrictions down here, I'm actually going to use the zero product property and say, okay, my restriction is going to be where x minus 4 times x plus 3 is equal to 0. And I'm going to separate these out. So x minus 4 is equal to 0 and x plus 3 is equal to 0. So here I'm actually going to have two domain restrictions because up here I was able to factor the denominator into two different quantities. So my restrictions are going to be a positive 4 and a negative 3. And in terms of the domain, when we have two domain restrictions, we always want to write the lesser value first and the higher value second. So my domain is going to be all real numbers except for negative 3 or positive 4. So negative infinity to negative 3, union negative 3 to 4, union 4 to infinity. And that's basically telling me that I'm getting from negative infinity to positive infinity, except I'm skipping over negative 3 and I'm skipping over positive 4. And what that would look like in set notation, x such that x is an element of the reals, x can't be equal to negative 3 or 4. And I can just list those out. X can't be equal to negative 3, 4. Okay, so example D, this one's going to be a little bit different because when we go to factor the denominator, we will notice that there's actually a common factor between the numerator and the denominator here. So this function can actually simplify, but the domain restrictions are always found before you simplify the function. So if you notice that there's something in common between the numerator and the denominator, you want to find your domain restrictions first and then go back and actually simplify your function. And we'll talk about that in 1 second. So again, the domain restriction is going to be where the denominator is equal to 0. Well, if you'll notice, our denominator is actually exactly the same as example C. So we have the factor of x minus 4 and the x plus 3. So that actually means that our domain restrictions are going to be exactly the same because we would split up, again, our factors using the zero product property in the exact same way. So our domain restrictions are still positive 4 and still negative 3. So the domain is actually exactly the same as example C. But up here, I'm going to go back and visit example D again. So now that we have our domain restrictions and we're saying, okay, the denominator here can't be positive 4 or negative 3, my function can actually simplify. And the way that I'm going to simplify it is like literally to cancel out these factors. So that's going to tell me that my simplified q of x divided by p of x here is actually going to be 1 over x plus 3. And we'll talk more about why these domain restrictions happen if the x minus 4s end up canceling out. That's going to be in a different unit. So again, when you're looking for your domain restrictions for something that does simplify, the domain restrictions always have to be found before you cancel out your factor. And we'll look at another one in example 2. All right, so example 2, we're letting f of x be x squared and we're letting g of x be 2x. and we want to find f divided by g, and we want to state the domain, and then we'll look at the opposite. So g divided by f, and we'll state the domain. So for example, A, again, this is just a different way of saying f of x divided by g of x. So this is going to tell me that that's going to be x squared divided by 2x. So our domain restriction is going to be where the denominator, again, is 0. So the domain restriction is going to be where 2x is equal to 0. And again, if I solve this out like I would a regular equation, that's going to tell me that x is equal to 0. So our domain restriction is going to be that x can't be equal to 0. So we're actually going to write it almost exactly the same, or actually exactly the same as example A above here, because that was our restriction here. So our domain is going to be negative infinity to 0, union 0 to infinity. Or in set notation, again, that would be x such that x is an element of the real numbers, and we know that x can't be equal to 0. But again, we do have a function that can't be simplified here. You'll notice that we really have a common factor of x in the numerator and the denominator. So that's going to really tell us that, remember that x squared is really just x times x. So that tells us we have x times x in the numerator, 2x in the denominator. One of our x's is actually going to end up canceling out. So our simplified function of f divided by g is actually just x over 2. Or if you want to write that as 1/2 x, that's exactly the same thing. All right, so let's look at the opposite. What if we divided g of x divided by f of x? So what if we put g of x of 2x on the top and f of x squared on the bottom? So again, we know that there's definitely going to be a common factor that we want to cancel here, but before we want to find our domain restriction. So again, that's going to be where our denominator is equal to 0. So that's going to be where x squared is equal to 0. Well, in order to solve here, we'd want to take the square root. Well, square root of x squared is just x, and the square root of 0 would just be 0. So actually, our domain restriction ends up being exactly the same as example A. So that means that we're just going to be skipping over the x value of 0. So negative infinity to 0, union 0 to infinity. Or again, in set notation, x such that x is an element of the real numbers, x can't be equal to 0. But back up here, again, we do still have that common factor that we had in example A. So that's really telling us that our numerator is 2x, our denominator is really x times x, because again, that's just a different way of writing x squared. When we cancel out one of the x's in the top and the bottom, that leaves us with 2 over x as our simplified function here. Okay, so that's kind of the idea with simplifying and finding domain restrictions. So we'll look at just kind of one more different type of an example where we can simplify, but it's actually not going to kind of look that different. So example A, we want to find f of x divided by g of x. So this time our f of x is 2x plus 12 over g of x is equal to 6. So 2x plus 12 over 6. So you're probably noticing here that our denominator actually doesn't have a variable in it. So if we tried to find a restriction here, that would be us setting 6 equal to 0. Well, we know that 6 can't ever be equal to 0 because 6 is 6. So in this case, when we end up getting something that looks like this, when like we get a restriction that doesn't make sense, I like to go back and look at the function again and say, okay, well, why? Why did this happen? Well, if you'll notice, our first term, 2x, actually has a common factor of 2 with the 6 in the denominator. And the second term of 12 actually also has a common factor of 6. So you'll notice that this is actually just 2x over 6 plus 12 over 6. And if you simplify that, that actually just gives us 1/3 x plus 2. If I take the 2 and then divide it by 6, I get 1/3. 12 divided by 6 gives me 2. So what is this telling us? Well, this is telling us that f of x divided by g of x is actually just a linear function. you'll notice that this is in like the mx plus b format. This is my slope and this is my y-intercept. So what that means is that a linear function actually always has a domain of all real numbers. So that's why this piece over here didn't make any sense. If I got 6 is equal to 0, well, that's because the domain probably has something else going on here. In this case, that just means that our function is linear because we were able to just kind of manipulate this a little bit and rewrite it a little bit different. So our domain is actually all real numbers here because it just ends up being a linear function. We'll notice that in example B, that's not the case because now we're looking for g of x divided by f of x. So g of x is 6, and then we're dividing it by the f of x of 2x plus 12. And this one's different because now we have that variable in the denominator that we're able to find a restriction for. Because when we set up our denominator equal to 0, to find our restriction, well, now we have a linear function that we can solve. Over here, we didn't have anything that we could solve because we didn't have a variable. So if I solve this, 2x is equal to negative 12, x is equal to negative 6. Here's the value that we want to skip over in our domain. So our domain would be all real numbers, except we would want to skip over negative 6. Or in set notation, that would be x such that x is an element of the real numbers. X can't be equal to negative 6. And actually, if we kind of notice back up here, we were able to simplify this function over here because we knew that these numbers all had common factors with each other. We can actually still simplify this. If we take out a common factor of 2, so if I rewrite the numerator as 2 times 3 and I factor out a 2 in the denominator, you'll notice that there's a common factor here of 2 that can cancel out. So we're just left with a 3 over an x plus 6. All right. So we'll just get into just some quick review of function operations, and then we'll look at just kind of a good summary chart of domains. So I'm just going to go through a couple of these pretty quickly. The f plus g of x and the f minus g of x we talked about last week. This g of x divided by h of x we just talked about. So remember that this notation of f plus g of x is really just saying that this is f of x plus g of x. So we know that f of x is 2x plus 1. G of x is x squared minus x minus 12. So when I combine my like terms here, this is going to give me an x squared plus x minus 11. I'll do my f minus g of x. That's really just telling me that I have f of x minus g of x. And again, when you're doing subtraction, you do have to make sure to keep that second function in a set of parentheses. So 2x plus 1 minus the quantity of x squared minus x minus 12. I'm going to distribute that out. So 2x plus 1 minus x squared plus x plus 12 is going to give me a simplified function of negative x squared plus 3x plus 13. G of x divided by h of x. So g of x is x squared minus x minus 12. H of x is x cubed minus 2x squared minus 15x. And again, I want to be thinking about, can I simplify this? So I definitely can factor up in the numerator. So that's going to be an x minus 4 and an x plus 3. Denominator, there is a actually common factor of x. So that's going to be x times x squared minus 2x minus 15. And this actually does factor further. So I'm going to rewrite this as, again, x minus 4 times x plus 3 in the top. And the bottom, x times, I think it's going to be x minus 5 and an x plus 3. So here is my function all written out in its factors. I do want to go back and state the domains of these functions. So I'll just kind of go back and look at example A and B, and then we'll talk about the domain of this one. Example A, our ending function is a quadratic. A quadratic function actually always has a domain of all real numbers, which we will summarize down below. So we'll look at example B and say, oh, hey, look, that's the same thing. So the domain here is actually going to be a quadratic. So its domain is also going to be all real numbers. Down here, I'm actually going to end up having 3 different domain restrictions because I have 3 different things going on in my denominator. So my restrictions here are going to be where x times x minus 5 times x plus 3 is equal to 0. So that means that I'd want to find where x is equal to 0, where x minus 5 is equal to 0, and where x plus 3 is equal to 0. So again, anytime that you have different quantities, different factors here, even though we see that we have something in common that we can cancel out, we always want to find our domain restrictions first. So that's going to be one domain restriction of x is equal to 0, a domain restriction of x is equal to 5, and a domain restriction of x is equal to -3 when I solve those out for x. So the domain, and I'm going to actually write it up here because I'm running out of room down there. So the domain is going to be where x can't be equal to 0, x can't be equal to 5, and x can't be equal to -3. But again, I'm going to rewrite that in ascending order. So -3 is going to come first. 0 is going to come second. And 5 is going to come third. So the interval notation for this one's a little bit long. We're going from -infinity, skipping over -3, skipping over 0, skipping over 5, and then going to positive infinity. In set notation, that would be just x such that x is an element of the real numbers. I would just write it as x can't be equal to -3, 0, 5. Okay. So we'll notice that down here, the operation is a little bit different. Instead of having an x here, we have a 3. Instead of having an x here, we have a -2. And instead of having an x here, we have a 6. So this is basically telling us that if we know what f plus g is, which we do because we actually just did f plus g up here, we would want to evaluate that quantity at 3. So we know that f plus g is x squared plus x minus 11. What this is asking us to do is take that x squared plus x minus 11, and we want to evaluate at x is equal to 3. That's what basically this is telling us what to do. It's telling us to take that f plus g up here, which we calculated, and it's telling us to evaluate at the x value of 3. So I'm just going to go ahead and plug in the 3. So 3 squared plus 3 minus 11, so 9 plus 3 minus 11. So that's going to give me 12 minus 11, which would just give me a 1 here. Similar thing here with E. So it's asking us to do f minus g and evaluate that at -2. Well, we already did f minus g up here. We know the f minus g is -x squared plus 3x plus 13. And that is asking us to evaluate this at x is equal to -2. So I'm going to go ahead and plug in -2, and I'm going to be careful here with my parentheses. So -2 squared plus 3 times -2 plus 13. This is going to tell me that this is a -4 because -2 squared is a +4, but I still have to carry down that negative outside. Minus 6 plus 13. So it's going to give me -10 plus 13, which will give me a +3. And then lastly, we're looking for f, which is g of x divided by h of x evaluated at 6. Well, up here, again, we didn't finish simplifying our function. Our simplified function, when we get rid of the x plus 3 and the x plus 3, is actually just going to be x minus 4, and then in the denominator, x times x minus 5. And this we want to take and we want to evaluate at 6. I think the 6 is coming from right here in the parentheses. So I'm going to plug in 6. So 6 minus 4 times 6 minus 5. So 6 minus 4 in the numerator is 2, divided by 6 times 1. So 2 over 6 would simplify to 1/3. All right. So we'll just kind of look at a quick summary of domains. I just want to go over this because on the homework, it's going to ask you to state the domain of your function. So a constant function, remember, is just like y is equal to 3 or y is equal to -2 or y is equal to 5. So a constant function looks something like this. And anytime we have a constant function, its domain is actually going to be all real numbers. Because I could take any x value along that line and get a real number. A linear function probably might look something like this. And a linear function always also has a domain of all real numbers. A quadratic function, again, is just a parabola. So it's going to either look something like this, or it could be that upside down. I would just kind of commented on, I think it was on the last page, that the quadratic functions always have a domain of all real numbers. We talked about cubic functions already this year. We know that the cubic function has sort of like an S shape to it. And a cubic function always has a domain of all real numbers. A quartic function is actually a degree 4 polynomial or degree 4 function. So it has something like an x to the 4th in it. That's the proper name for an x to the 4th is called a quartic. The quartic function actually behaves pretty similar to the parabola or the quadratic function. It actually probably looks mostly the same. A lot of times the quartic is a little bit more spread out, but it should look something like a parabola most times. So any degree 4 polynomial actually always has an all real numbers for a domain. The rational or the fraction function, so like the ones like we were working with in example C, we know that their domains are a little bit different. So we have to restrict, and we're going to talk about the actual graph a little bit later in later units. So we wanted to restrict the domain by setting the denominator equal to 0. So that's kind of the difference. So basically any other function that you might run into, so a constant, linear, quadratic, cubic, or quartic, basically all their domains are all real numbers. The only one that's going to be different and the one that we have to be careful about is going to be the rational function. All right, we'll look at one more example. This one's a little bit different because it does have a square root in it. So we want to say f of x is equal to the square root of x minus 3 and g of x is x minus 5. So if we want to divide f by g, that's going to tell us that we have the square root of x minus 3 divided by x minus 5. So we want to state the domain. Again, the restriction is going to come from the denominator. So x minus 5. And we want to set that equal to 0. So if I solve that out, that's going to tell me that my restriction is x is equal to 5. So that's going to be the value that I want to skip over. So my domain is going to be all real numbers except for 5. So negative infinity to 5, union 5 to infinity, or in set notation, x such that x is the element of the reals, x can't be equal to 5. You'll notice that in example B, though, when we divide g by f, x minus 5 divided by x minus 3, now the square root is in the denominator. So we haven't talked about square root functions yet this year, but we have to think about this in terms of the restriction and what can go into that denominator. So we know that the square root of x minus 3 can't be equal to 0 because we know that we can't have a 0 in the denominator. But we also have to be careful because we know that we never can have a negative number underneath a square root. Because remember that you can't take a square root of a negative number, it's not a real number. So not only can the denominator can't be equal to 0, but it always has to be positive under the square root. So how do we get that? How do we get something that can't be equal to 0 and we need to make sure that it's always positive underneath the root? Well, in this case, what that's going to tell us is that the stuff under the square root has to be greater than 0. So it can't be equal to 0. So we can't put the equals to symbol over there because we know that if it's equal to 0, we're going to get a 0 in the denominator. And we have to make sure that the stuff is always going to be positive. So to ensure that, to make sure it's positive, we have to make sure it's greater than 0. So with the square root, our restriction is going to be where x minus 3, the stuff underneath the root, is greater than 0. So when I solve that out and I add 3 to both sides, that's going to tell me that x has to be greater than 3. So what that means is that when I write my domain, the domain basically says that I have to get all x values greater than 3, and that's it. So in terms of interval notation, that's going to tell us that we're starting at positive 3. I'm not including it because if I included it, 3 minus 3 over here would be equal to 0, and we can't have that. And we're going all positive, so we're going to infinity. In set notation, that would be x such that x is an element of the real numbers. X would be greater than 3. And again, we can test that. We know x has to be greater than 3. Well, if I plugged in a 4 here, 4 minus 3 is 1. That gives us a 1 in the denominator. That gives us something that's non-negative underneath the root. If x is greater than 3, I could plug in a 10 here. 10 minus 3 gives me 7. That works. If I plugged in anything less than 3, if I plugged in a 2 here, that would give me 2 minus 3, which is a negative 1. We can't have a negative underneath the root. If I tried another number less than 3, how about 0? 0 minus 3 gives me a negative 3. Again, I can't have a negative underneath the root. So when you have a square root in the denominator, these are the two things that you really have to remember. The denominator can't be 0, and the stuff underneath the root always has to be positive. Okay, so it's your turn to do some practice on the homework. Please let me know if you have any questions.